All right, so on example 3, how would you read that? F of g of h of x. Fogo. Fogo. Yeah, Fogo. F of g of h of x. Let's give it a name. W for wild, crazy Fogo of x. Okay, so the condensed notation is F of g of h of x. Now, to write it in the expanded form, that's going to be F of g of h of x, close, close, close. Describing my daughter's closet. All right. Okay, so now you could take it all at one time and plug it in without the f, g, and h in it, but in this case, since it's a triple, we're not used to triples, we're used to doubles. I'm going to go ahead and just kind of do it piece by piece. So I'm going to leave the outer layer as just f of something. And I'll focus on the g of h of x first, g of h of x. So that means I'm going to take the g function, which is x to the 20th, and I'm going to plug in my x plus 5 for x. So it's going to be x to the 20th, and then I'm plugging in the h of x, so that's x plus 5. Now, before we go to the next layer with f, should we simplify that? Or do you want to simplify that? Yeah, me neither. Expanding it is not just x to the 20th plus 5 to the 20th. Remember, that would be foiling it 20 times. Ugh, ugh, ugh. All right, that might take you like the whole Christmas break to do that. So we'll just save it for then. I'll assign it over Christmas break. Right now, we'll just leave it as x plus 5 to the 20th. That would be like my Christmas gift to y'all. Okay, now we're going to plug that into f. F has two inputs, one in the numerator, one in the denominator. So that is going to be x plus 5 to the 20th all over x plus 5 to the 20th plus 1. And now you get excited. Ooh, ooh, ooh. Does that work? No. It's a term in the bottom. It's a factor in the top. So really, you're pretty much done. You're pretty much done unless you want to expand it out. Can we find the domain, though? Yeah, the domain of W. We don't have a radical, but we got ourselves a denominator with a variable in it. Is x plus 5 to the 20th plus 1 ever 0? Ooh. When x is negative 5, it gets close. The smallest it gets is what? 1, which is still safely far enough away from 0. So the smallest value it gets is 1. 1 is not 0, and then it gets positive after that because it's raised to the 20th power. That's an even power, right? So it's going to be a positive number. So the domain should be all real numbers. That's right. That's the domain of W. Sweet. So that one was kind of anticlimactic. I thought it was going to be more fun because it was like a triple composition, but it turned out to be just mediocre. All right. Hey, look, hard to refute. Going forward is one thing. Not two things. One thing, going forward. Going backwards is yet another thing. So that would be two things, right? Forward, 1, backwards, 2. I don't know what that means. Why is that there? Oh, it's a segue. I get it. What we're doing on example 4 now is instead of composing, like we did up here on F, G, H, and I, me give you some functions and you put them together. Now I'm giving you something that is put together, and you're going to give me the components. We're going to decompose it, right? Yeah. So we're starting with something that is all put together. H of x is the cube root of x minus 8, and it says to decompose it into two non-trivial functions f and g, such that h is equal to f of g of x. All right, first things first. Recognize that g of x is the inside function, and f of x is the outside function. G of x is the inside function, f is the outside function. Now, what the heck does non-trivial mean? I'll show you what trivial looks like. The first trivial, there's two trivial decompositions. The first one would be if you let g of x equal x and let f of x equal the cube root of x minus 8. Now, when you compose it, f of g, that means you're going to take this x right here and replace it with x. Ooh. That's trivial, okay? Because that's easy. You're not really replacing anything. So that would be the first trivial one. The second trivial one would be if you let g of x equal the cube root of x minus 8, the whole thing, and then let the outer function equal x. Because now it says take this x on f of x and replace it with the cube root of x minus 8. Ooh. Those are fantastically wonderful. These are your two trivial ones. Why are they trivial? They're easy. They're too easy, okay? What makes them trivial is anytime you have one of your inside functions being just plain old x, that's trivial. Because then the other one is just a plain old original thing. So don't give me trivial ones. You can give me obvious ones, but don't give me trivial ones. All right, so it might be easier to start with naming an inside function. We're going to have to come up with at least two, it says. So what could I call g of x, the inside function? If you look at the cube root of x minus 8, what does it mean to be inside the cube root function? It means to be under the radical, right? What do we have under the radical? X minus 8. That's not trivial, because x minus 8 is not x. So if the inside function is x minus 8, the outside function could be just the cube root of x. Yeah. So that would be the obvious one. And I would accept that. It's not trivial. Because this says now you're going to take the x under the cube root and replace it with x minus 8. And boom, you end up with the cube root of x minus 8. Excellent. Well done. But we need another one now. Anyone have another one? I'll write it out here. G of x and f of x. I'm ready to go. I'm ready for your input. When you all speak at one time, I can't hear any of you. You're going to have to take turns. I don't know. Let's just call this one x minus 3. I made it up. Instead of x minus 8, I just took half of the 8 away, namely the left side. You got 3. What would the outside function then have to be so that when I plugged it in, I ended up with an x minus 8 instead of an x minus 3? X minus 5. Muy bien, right? Now you're going to take this little x down here, replace it with x minus 3, and you get x minus 3 minus 5. What's minus 3 minus 5? Minus 8. Oh man, that opened up a whole new category for us of non-trivial ones. For ejemplo, what if I let g of x equal x plus 2? Now f of x would have to be equal to the cube root of x minus 10. So that when I plug in a positive 2, the minus 10 is right there to make sure I get a negative 8. So how many are there of this variety? Infinitely many of them. You should be able to come up with 2. So that's a whole vein right there of solutions, of decompositions. Does anyone have like a different track to get on? Instead of like adding something to the inside function. Was that multiply and divide? Yeah, what if I call the inside function 2x or the outside function 2x? What would the inside function need to be so that when I plugged it in and doubled it, yeah, it would need to be 1/2 x minus 16 or 4, right, the other way. You caught that, right? And you can always do trial and error. You can pick a function, compose it. If it works, great. If not, see why it doesn't work, come back and adjust it. Now if I plug 1/2 x minus 4 in for x and distribute the 2, I get an x. Oh, it'd be cube root. Yeah, not square root. Thank you. Cube root. And I distribute the 2, I get x minus 8 under the radical. So that is a whole nother vein. If you want to let the outside function be the cube root of 3x, this will be 1/3 x minus 8/3, so on and so forth. So infinitely more based upon that. Let's come up with one more type of answer. And I think that would be enough of the infinity many of them. What if I let my inside function be the square root of x? Then the outside function would have to be the cube root of x squared minus 8. Yeah. So you could do it with addition, subtraction. You could do it with multiplication, division. You can even do it with exponentiation. If I'm going to let the inside function be the square root of x, that could be x cubed. If I let the inside function be the cube root of x, that could be x cubed. So that when I plug it in, I'm going to end up with just plain old x. So there's a whole other vein right there. Infinity times 3. That's a lot. Anybody else have any other idea before we move on? You get to practice these in the worksheet. Okay, maybe in the worksheet you have time to kind of explore on your own in your math lab. You come up with some and then share them with the group later. Share the stuff that you make in your math lab with your friends. Okay. And if they want more, they know where to come to get more. Okay. All right, so now we're going to kind of shift gears here. Example 5. We're going to be talking about magic. Okay? So, let's say I'm choosing an integer between 4.5 and 5.5. I'm not going to tell you what it is, but I'm thinking of an integer between 4.5 and 5.5. Now, here's what I'm going to do. I'm going to take my number that I'm not telling you what it is. I'll call it x for now. I'm going to add 3 to it. I'm going to quadruple that number. And then I'm going to subtract 4 from that. And then I'm going to divide by 2. I'll give you that number. That number was 14. Could you, knowing how I got to 14, work backwards and get my original number that I was so selfish and didn't tell you? Yes, you could. In general, you could take the number I give you, which I'm going to call x, again, and what would be the first thing you would do if you were working backwards? You would have to multiply by 2, right? If the last thing I did to get to 14 was divide by 2, the first thing that you're going to do is multiply by 2. Then you would do what to that? Add 4, right? The second to last thing I did was subtract 4, so the second thing you're going to do is add the 4 back. Then what would you do with that quantity? You would divide it by 4 because I multiplied by 4. You would divide the whole thing by 4. And then, of course, if the first thing I did was add 3, the last thing you're going to do is subtract 3 from the whole thing. So let's see what my original number is. Does anyone know what it is right away? Let's see. Plug in a 14. What's 14 times 2? 28. 28 plus 4? 32. 32 divided by 4? 8. 8 minus 3? 5. Well done. That was my number. Y'all are good. Did anyone know what it was right away? How'd you know, Tillman? Oh, you just knew it. Oh, okay, good, good. No one thought that the only integer between 4.5 and 5.5 is 5? That's another way to get it. Oh, there is only one integer between 4.5 and 5. It's 5. Yeah, yeah. So cool. You could have done it that way too. It's basically me telling you, hey, my magic number is 5, but I'm not going to tell you. But you could also do it this way. This way is definitely more fun. This, like, you could set this kind of stuff up at, like, one of the booths at the Comal County fair, right? Someone would pay, like, $1 to do this. This, oh, highlighter. I hate when I do that. This is called Y. It takes a number and sends it somewhere. This undoes the work of Y. We call it Y to the negative first. Not really. That's how we write it. But guess what we call that? Yeah, we call that Y inverse. So now we're going to be talking about inverse functions. What do inverse functions do? They deconstruct or undo the work done by their inverse function. Okay? They don't fight over who's the inverse any more than you fight with your siblings over who the sibling is, right? They are inverses of each other, and they undo each other's work. So this is one way to find inverse functions. You can just logic through it. It was very intuitive there to do the reverse order with the inverse operations, right? If I multiplied, you divided. If I added, you subtracted. And you do it in the reverse order. So that means that these functions here are invertible. Not all functions are invertible. Invertible means that there is a way to undo the function. If you think of the function as like a wood chipper, you put in a log, you get out wood chips. Is there then a machine you can put the wood chips in and get the log back out? No. Unfortunately, I think a wood chipper kind of destroys everything that you put into it. You can't get it back out. So we would say wood chipper is a non-invertible function. But some functions are invertible. You can get things back. Like I dropped in my 5. Oh, no, I got out my 14. I just find the inverse machine, drop in my 14, and now I get back my beloved 5. I get back my beloved 5. Okay, so how are we going to know if a function is invertible or not? Well, think about it. If we're able to get the number back, then that means for every x, there's one y, and then for that y, there's only one x. 1 to 1. We've already talked about it briefly. Yeah, 1 to 1. A function that is 1 to 1 passes what line test? Horizontal line test. Yeah. Several of our parent functions are 1 to 1, like x, x cubed, e to the x, 1 over x. Those are all invertible functions. They have inverse relations that are also functions. There's only one way to code a number and only one way to decode it. We call that inverse f inverse or y inverse, or the inverse function. Now, notice what this looks like. On the graph, then, of a function f, there is a point a, b. And so what the function would do, it would take an a, turn it into a b. So on f inverse, that means you would input a b and get back your a. So notice what we're doing to get from a function to its inverse. ab becomes ba. We are interchanging x and y. Interchanging x and y. Everything xe about one becomes ye about the other, and vice versa. We call these 2 points on the inverses, we call these corresponding points. Corresponding points. So like up here on ours, when I dropped in a 5 over here to y, I got out a 14. When we dropped in a 14, we got out a 5. We would then call for these inverses, we would call those 2 points what? Corresponding. They're not the same points, they're corresponding points. Now you could have a corresponding point being the same, right? The point 1, 1, when you flip it around, is still 1, 1. But these are corresponding points. Now sometimes finding the inverse by the intuition method, like we did up here, is a little bit time consuming or it's not real obvious. So we're going to come up with an algebraic strategy. And that takes us to example 6. It says, determine if 4x minus 2 is invertible. How are we going to determine if this function is invertible or not? What's that? Yeah, we got to graph it and see if it passes the horizontal line test. So this is a line with the slope of negative, or the y-intercept of negative 2, and the slope of 4. So it looks something like that. It's linear. You probably could have told that without graphing it, right? Does a linear function pass the horizontal line test? Yeah, if it's a slanted line. If it's a horizontal line, no, then it fails about as bad as you can. But this is a slanted line, so it passes. So what we want to do then is find f inverse algebraically. So here's how we do it. Write out the function 4x minus 2. Step 1, replace f of x with what f of x is actually representing, a y value. It's easier to work with x's and y's. Now the next step is the most important. It's the money step. I use green for it. Cha-ching. Like we did with the ordered pairs for the corresponding points, you're going to interchange x and y. You're going to switch them out. So you get x equals 4y minus 2. Interchange x and y, and then you're just going to resolve for y. Now the reason this works is when you solve algebraically for y now, you're going to be doing the inverse operations in the reverse order. You're just doing it systematically like you were trained in algebra. So if you add 2 to both sides, you get that, and you divide everything through by 4, you get x plus 2 over 4. Now that we found the inverse, we're going to go ahead and rename it f inverse of x, and I'll go ahead and clean it up. I'll put both terms over 4. X over 4 plus 2 over 4 That's 1/4 x plus 2/4, which is a half. Now that's the graph of another line. Let's go ahead and sketch it. It has a y-intercept of 1/2 and a slope of 1/4. So it looks kind of like this. That would be the graph of f inverse. All right, so what's f of 2? Let's figure that out real quickly. What's f of 2? 4 times 2 is 8. 8 minus 2 is 6. So if there's a point called 2, 6 on the graph of f, what is the point on the graph of the inverse that corresponds to it? F inverse of 6 must equal what? 2. Yeah, and you could verify that right here. If you plug in a 6 for x, 6/4 is the same as 3/2. 3/2 plus 1/2 is 4/2, also known as 2. Now the last thing I want you to do before the bell gets us, we got 2 minutes left. Notice the slope of f was 4. See that? The slope of f was 4. What was the slope of the inverse? 1/4. How are 4 and 1/4 related? They're reciprocals of each other. I wonder if that's a coinky-dink or if there's something to that. Now, one last thing. Turn your head at a 45-degree angle to the right. I always thought that would make a good yearbook photo from my perspective if everyone was doing it. But not everyone did it, so good thing I didn't have my camera. I'll do it. If you turn your head 45 degrees to the right, what do you notice about the green graph and the blue graph? You could apparently fold this on the line y equals x, and the graphs would coincide with each other, right? Hey, let's dance, everybody. That is not a coincidence. If you have an inverse graph, it is going to be the reflection across the magical line y equals x, okay? That's how you get the graph of an inverse. We know how to do it algebraically. Switch x and y, resolve for y. Graphically, reflect across the line y equals x. We'll figure out why that works on Monday. Don't forget your Halloween story. I'm going to be prepared to be spooked.